Hey everybody, how are we doing? Good morning, good afternoon. Depends on what time it is for you. So if you're here in the chat, feel free to say, hey, Mewbot's here giving out those points. We're going to start off some activity here. Just going to mention something briefly. Let's go check it out. So I did a competition with my time series class. You can see the competition behind me. And the winning group had answers that were pretty close. I should have posted the actual answers on here too. But here was my predictions versus theirs. And you can see my predictions in blue, and that's group 5 right there. Very, very close predictions. I should post the actual. We might actually be able to do that. Let me do that real quick right here. I think I can auto layer it on here. I'm going to try to auto layer this really, really quickly. I've got the code. We're going to take a look at this, and then we're going to hop into our actual work right here and start doing. But this code right here is so nice, the code we work with. Should be able to go to auto layer. I added a guides, but I hadn't got that working yet. So let's go here to auto layer, because we know the answers to this. So if we know the answers, we can post the answers. And let's just try to see if we can get it to work with an auto layer. So auto layering the actual answers right here, the answers and the actual. I think it's gonna work. Oh, it's mad. Oh, because I did the wrong thing. I did a plus instead of a comma. And then we're gonna take a look at the activity here. We'll put the actual answers in orange right here. And I think it has worked. Cool. So let's see right here. Nothing's bad on the screen. Let's go take a look. So here we go. There's the code, and I'm actually just adding in the answers from the actual and doing a color right there. And so we can see the different ones right here. I wanted to add in some things, but so little bits of differences. Our models are very similar, both groups. So in case a time series person is watching, I did a lambda transformation. They know about that. But the orange is pretty close. We missed some of the variation down here, but this is predictive modeling, making predictions for quarterly sales. And our models are pretty good, pretty close to what's going on actual, except in this area, we have a pretty bad residual. We are going to be below the actual, so we have negative residuals. All your topics you're learning right now, if you're in BAS 320, it's kind of a future look right here, but everything you're learning about residuals and making predictions all carries over. And you'll learn how to work with this code right here. But this is like the time series of data behind me right here, and we're predicting the future. I'd say our models are pretty good. All those lines look to kind of blend together till you zoom in and you see, ooh, that region right here with the actual model, all of our predictions are a little bit low. Doing pretty well on these peaks right here because it is quarterly data. So I really like this code right here, and this is a little peek into time series and the code we use in time series. You might see some RMSE up there. Typical miss the model makes. Let's hop back to it. That's a little peek into the future right there. If you're thinking of taking time series, you'll hear topics again like root mean squared error. How did I bump the camera? You can see the screen on the edge of the corner right there. Let me fix this as we're talking right here. Put a little music. Somehow I bumped the camera today. So let's fix that. Oh, wrong button there. I've forgotten all the quick keys. There we go. Now the camera's no longer in the screen. Be careful, turn on the camera. So with this right here, let's hop over to the main screen and start doing some of your assignment. Let me clear this up right here. We're going to clear the environment. And here we go. If you're in the chat, feel free to say hi. We're going to start some activity right now. Let's do it. Okay, so we're dealing with categorical variables today. And you might say, well, wait a minute, we can't deal with categorical variables, but we can. Categorical variables can be dealt with when we turn them into indicator variables. So we're going to deal with categorical variables, something like, is someone an undergraduate or graduate student? We can turn that into zeros and ones to indicate whether someone is an undergraduate or is not an undergraduate. We're going to deal with the baby birth weight baby set, though. So the first thing you want to do is make sure you have library reg class loaded up. And so library reg class is loaded up, and we probably do that up here. And with library reg class loaded up, you have access to these data sets which are inside of it. Probably type it out, and you can see that reg class is right here. This is not loading a CSV or an Excel file for you. This is loading something that is like preloaded into R, and you have to make sure you have reg class on because this is inside the reg class dataset, as is example number 9, NFL. There's other data sets, like the Iris data set right here, which is just in the data sets. Lots and lots. I've got the AUS data set, the Australian production. So these are the data sets I was working with, and you can see what libraries they are inside of right there. You won't see these unless you've installed Tisble's data or FPP3. So we're not working with those today, though. We're working with the EX9 birth weights. Now, we're then taking this, which already exists, and just giving it an easier name. That's the whole point of that right there. So technically, you could go here and do remove, and now it's gone. It's gone. Just removing the EX9, kind of cleaning up our global environment a little bit so we only see the baby data set right there. Smoker has 2 levels, now and never. Are smokers or are non-smokers the reference level? I used to just be like, oh my gosh, got to put this in like reference level is first. I am first. Logistic last. Repeat that to yourself. If you're watching this video right now, repeat to yourself, I am first. Logistic last. Now, what does this all mean? When making indicators, the reference level is first alphabetical. So when you say I am first, in indicators, the reference level is the first level. So we'll look at that in a moment, and first alphabetical, and it'll be never, I believe. We'll double check as we make our models. A, B, C, D, E. E comes first, and they both have N at the start. So never will be the reference level. And we'll talk more about reference levels here in a moment. We haven't done logistic. It's got an IC at the end. But in logistic, the level of interest is last alphabetical. So it's a little bit confusing. A lot of people, it's just memorization. It's putting it down on your cheat sheet. If I ask you what would be the level of interest here, it would be now if we're predicting it. And logistic is categorical Y. And indicators are categorical X's. We haven't done logistic yet, but this is a good... Hey, Ditto, good to see you here. Ditto, 100 points. This is a little bit of future-proofing right here. If you ever hear me say a reference level, I'm talking about an indicator variable has to be associated with a reference level. Like, you have to compare it to something. We often talk about my family, and we'll erase this right here, but Brian would be the reference level in his family because Brian has a B in his name, and there's no one with A's or a B before Brian. Brian has an age of 39. And Brian actually would not have any sort of coefficient. Emily has a coefficient of -2, and Darren has a coefficient of +3. So when you think about it, we are comparing everyone to Brian. So we know Brian is 39, Darren is 3 years older. We could also figure out, so Darren's 42, we could also figure out there is a 5-year difference between Darren and Emily because you could subtract the levels. So Brian is the reference Y again because Brian is first. It's not quite how we do it, but it's a good example to understand how would we assign the reference level right here. Brian would kind of be the reference child. I'm also the reference person. I've got the first alphabetical name in my family. So everyone would be compared to Brian. So when we do comparisons right here for this data, we are going to compare now to never. Like now we'll get an indicator. And so let's put this right here. Indicator. And this will be the reference. Now, one thing to always know about this, there is always only one reference level. So Ditto right here, help us out. If we have day of the week with Monday, Tuesday, Wednesday, Thursday, Friday, I guess I could write them all out. Monday, Tuesday, Wednesday, Thursday, Friday, Saturday, Sunday, what would be the reference day of the week? Good question right here. What would be the reference day of the week? And there's only one reference day of the week. It's the first alphabetical anytime you do it. Really good practice right here to know it instantaneously. If we're going to compare data that has days of the week in it, we would have one reference day of the week. And that reference day of the week would be what? Not Monday. Not Monday. Good guess right there. 100 points. Not Monday. How do we choose the reference level? Not Monday. Oh, I should have put... Got to put that right there. It says it right here. I'll put that as a reminder. So it will be the reference day of the week. Good practice. Good practice to make sure we remember the topics. So don't worry. We get it wrong here to get it right on the test. So the reference day of the week, and then why, it would be this. It's Friday. It's today. Not because it's today. Then it's Friday because it's first alphabetical. So everything else would get indicators. So this will have an indicator. So everything else gets an indicator. There will be 6 indicators. I can't count days of the week. There'll be 6 indicators because there is one reference. Every other day of the week will be compared to this. Every other day of the week. Yeah, it is today. It's Friday. So now we're actually going to make these models right here. Kind of I'll put a point right here. Like, this is how to find the reference level. Pretty good. What will be the reference month of the year? We just do this as quick practice. What will be the reference month of the year? If you can solve these problems, you understand how to solve what the reference level is. What will be if we have data with months of the year? We're like, oh, this was collected in February, this collected in January, this collected in April, this collected in August. What will be the reference month of the year and why? A little more to write on here than what I'd want. Oh, I need to go off top chat and go to live chat. What will be the reference month of the year? Like, if you have all the months of the year, the reference month of the year by default assignment, which is first alphabetical, the reference month of the year would be what? Good practice. April, great job, ditto right there. And then there'd be 11 indicators for every other month. And we'll see this right here. Our data is going to have only one indicator. Great job, ditto, 100 points right there. And so we need to fit a model. It says fit a model. So we're going to fit a linear model right here, save it into object M, predicting birth weight. One best thing you can do is just copy paste. From only smoking. Ooh. Y tilde X comma data equals. And the data is equal to, we saved it into baby right there. Should work. There it goes. Go away, X. There you go. Bye-bye. And now we're going to do a summary of the model to take a look at what's going on. Now, you'll notice it says smoking now. But smoking now is the variable name, smoking with the level now. So what we see right here, and this is pretty interesting, is we actually see the difference between the birth weights of mothers who are currently smoking. I guess they smoke at some point because it's smoking now or smoking never. So those are not really complements of each other, but we'll just say these are the smoking mothers when they say they're smoking now. And then the other mothers are not smoking, even though it says smoking never. Like, are you smoking currently? I never smoke. So you either smoke now or never smoke. With this right here, this is the difference between two mothers where one mother is smoking now and the other mother is smoking never. And this is in grams right here. Let's ask Siri right here. What is 271 grams to pounds?
The answer is 0.6 pounds.
I don't know if you heard that. It's 0.6 pounds. It's about a half a pound difference. So babies born to mothers who are smoking now would be expected, like two mothers who are having a baby. That's how we do it. Two mothers who are having a baby, where one who is smoking, let's write this out. I'm going to put this right here. Interpretation. Two mothers who are having babies, where one is smoking now, and that is the indicator, and the other is smoking never, reference. The mother who is smoking now is expected to have a baby that is 271.77 grams lighter. I think that's how you spell it. Smaller than the mother who is smoking never. So important to know here, we compare the indicator to the reference level. And what's really interesting about this, and I think we go through this maybe a little bit here, is if you were to compare these babies, I think we can write a quick command right here. Let's go to aggregate and take birth weight by smoking. And I want you to see something as we look at this model. And we could just run the whole thing right here. It should work. There we go. So these are the means for these two groups. And what do you notice right here? The intercept. The intercept is actually the value for the reference level. So don't worry about, you don't have to write this command I wrote, but it's kind of showing us something. We have right here, we aggregated the data, looking at the birth weights, splitting it apart by whether or not someone smokes for the baby data set, and we ran the function mean. So you could change this function and run something else and get different means for different, or to get the mean, the standard deviation, just depending on if you change this function. But the important thing to note right here is that this is the intercept. But if someone is smoking, what do you think the difference between these two numbers are? Like 348 3482.114. And this number right here, I'm going to try to do it in my head. You ready? Decimal differences might come into play, but right there. 271 point and it rounds to 77. And look at this. The mothers who are smoking now, we see on average that their babies are 271.77 grams lighter, which would be a prediction of 3,210 grams, 0.379. So when we're looking at this right here, this model currently doesn't have any other X's in it. So we would just make the predictions for the mean. So these are, interestingly enough, also the naive models for the mean of just the smoking now group and the smoking never group. Now you might say, why don't I see smoking never up here in this data? And once again, we got to remember that that is the reference level. That is the reference level. So if a mother was smoking now, let's write this model. Good practice right here, write the model. So you should be able to do these things right here. Try to pause the video, maybe try to write the model along. See if you could write the model. We need to take this. So we'll say birth weight equals this plus this. So this is actually a minus, not a plus today, times this. And if this is the full model here, what if a mother is smoking? So if a mother is smoking, model smoking, for smoking, let's say, what would we plug in? So ditto, if you're still here, what would we plug in for a mother who is smoking? I'll make this look a lot nicer here. What would we plug in for that indicator? These are the key things to know. Indicators can only take on two values. So what would we plug in for the indicator to indicate a mother is smoking? To indicate a mother is smoking, we would plug in what to the indicator variable and then kind of reduce our equation down. So what would we plug into the indicator to indicate that a mother is smoking? Here. Indicators can only take on the values of 1 or 0. So if a mother is smoking, which is the line we're going to solve for right here, we'd plug in 1. And so now we're just going to reduce this equation down, and I can already tell you mathematically we get this. You just solve this out right here. Mathematically, you get this. What would we do if we had a model to write for never smoking? The never smoking would get a 0 for this, and this one's really easy to solve. Hey, Anna, good to see you here. Ask any questions you have. We're showing how to write the implicit lines right now by solving, putting in the values of the indicator as 0s or 1s. These can only take on values of 0 or 1s if they're an indicator variable. And so now we're just plugging in the mother is never smoking. We have here a 0 for the value that the mother is never, because smoking now would be 0 because they're not smoking now. So we plug in a 0 and we get the mean of the never group right here. So we wrote out the full equation and we've interpreted it, all this good stuff right here, and we've got all the coefficients. Ask any questions you have. Q2B, here we'll pause right here. This is going to be a similar thing to what we just did. We're going to look at the associate command right here. So let's take a look at it. Ask all those questions, Q2B right here. Run the associate, taking the Y with the birth weight and the smoking. So we're actually doing almost the same identical work. So the great thing is you can kind of grab your data from here, and we're just going to go down here and take it and run associate. And here we are. Now, this is just another way to get the same answers we just saw. And look at what we get. What we get right here is the mean for the never group is 3482.144. It doesn't show the decimals. And then we get the mean for the now group is 3210. And these are the same answers we've been getting. So what you'll notice is this is just a difference in the means. It's just if the mother is smoking now, we'd expect the baby to weigh this much. But if the mother is smoking never, we'd expect the baby to weigh this much. And this difference, once again, is the difference right here. This difference is the difference between the means that we are observing in the groups. So that's what this model is doing. It's allowing us to use a categorical variable to talk about the difference between the means. And so now, is the overall difference statistically significant? Well, let's look at the p-value. Anytime we want to know if something is statistically significant, we would take a look at the p-value, and yes. Now, we could have easily looked at our model also, and the answer is yes for our model too. Yes, for the variable in the model, this is very, very, very statistically significant. And then the question becomes, is this practically significant? Babies generally weigh, or we could do a mean for baby weight. So it says right here, a gram is 450 pounds. So let's take the mean for baby, $ birth weight, and that's the mean of it. And the average baby right here weighed 7.5 pounds. So what we're seeing right here is a difference in baby weights of about 0.6 pounds. And how do I know that? This difference right here, the coefficient that we see right here is the difference. And let's divide that by 450. And so with your babies being about 7.5 pounds, if the babies for the smoking mothers are expected, not will, never say that will word, are expected to be over a half a pound lighter, is that a big difference? I'd say yes. There's, especially when it comes to premature babies, a half a pound difference is huge. 1 pound difference in babies is pretty big too. Just that's pretty crazy to think, like a pound. Like, you know, we might gain a pound a day or something. But for a baby especially, a pound is a big amount of weight. It can be, you know, over 10% of its weight, closer to 20% of its weight, especially for babies around 5 pounds. So this is a massive change to a baby's weight, close to maybe around 10% of a difference between the baby's weights, 8 or 9%. We could find out by comparison to the average baby, which we found the average baby right there. This is a difference of around 8% of their weight. So that's how we might communicate that to someone. Remember, practical significance is always in the eye of the beholder. You might say, like if I told you, you might gain a half a pound next month, you might be like, so what? If I told you next month your baby might lose half a pound, you might say, oh no, because that in comparison to a baby in that context, it is going to be much more practically significant. Once again, there is no threshold for practical significance. It's the literal, do you care about it? And you as a person looking through the data would have to communicate, why do we care? You have to make the case by saying, well, the average baby weighs 7.5 pounds. We're seeing a difference of about 0.6 pounds here, which is about 8% of the overall weight when we compare it to average babies, which is a pretty big difference, which is very statistically significant and I think practically significant. Someone might be like, I don't care about it. That'd be their prerogative. And so we did that right there. We need to slow down. We're doing a great job right here. If you have questions, let me know. But I like working with data. It's so much fun. Let's hop into question number 3. Take a little more coffee right here. Got our morning coffee. Hope everyone's doing all right. Put on a little chill music. If you have questions, let me know. Just building some models and interpreting coefficients. That's what we do. Question number 3. The observed differences in birth weights could be attributed to smoking, but it could be other variables, especially like gestation. Gestation is how long, and it says right there, gestation is how long you are pregnant for. And just think about it. We know these things about the world. We know that mothers who are pregnant longer would be expected to have heavier weighted babies. It doesn't mean if you're pregnant for 9 months, you will have a larger baby than other people, but we would expect 2 mothers who are otherwise identical, where one has a longer pregnancy than the other, we'd expect the mother who has a longer pregnancy to have a heavier baby. So now we want to fit a model with these variables. So let's go in here. And what's important about multiple regression right here, we're just going to grab this, do our little tilde, and do plus. What's important about doing a multiple regression is the interpretation, is that 2 mothers who are otherwise identical, but one is smoking and one is never smoking. That means the mothers who are otherwise identical had the same length of pregnancy. We're comparing 2 mothers who had the same length of pregnancy. So you might say, well, mothers who smoke have shorter pregnancies. That doesn't matter. Rock, he knows what's up.
It doesn't matter.
That's not what matters in the interpretation, because the mathematics of it only changed smoking or not smoking. And we would be able to isolate that variation and control for how long the pregnancies are. So this is going to compare equal mothers right here who have the same length pregnancy. And that's what's so important. Someone can't say, well, smoking makes your pregnancy shorter. Even if it does, we're going to compare mothers of equal pregnancy for both groups, and we can see the impact right here of smoking. And does smoking still impact the model? The answer is most definitely yes. But as you might think, gestation is even more statistically significant. We see right here, I think this is in terms of, let's look at gestation. Gestation is in terms of weeks, I believe. And so this is how many grams, like two mothers who are otherwise identical, like they both would either be smoking or not smoking, like if we're interpreting gestation, but differ in their gestation by 1 week. The mother who has a longer gestation is expected to have a baby that is 91 grams heavier than the mother with the shorter gestation. Make sure to know your interpretations. Two mothers who are otherwise identical, who I'm trying to figure out to a number for some. Yep, that's it. That's it, Ditto. Great job, Ditto. Yep. Make your models and find the best ones. And we did it during one of the office hours. So check one of the recent, like I think Wednesdays. Check one of those. We did the 4-year models. Good stuff right there at the 4-year models. Oh, did you see the start of the stream? I showed which people won. Good guess there, Ditto. I ran your things from the Discord. Good guesses. I showed it at the start of the stream. I don't have it up anymore, but I go to the very start. I show the models and I add on the actuals. We were pretty close. We had some bad residuals in the 5th and 6th quarter time, though. Pretty good model, though. Same sort of stuff we're doing here with residuals. It all adds up. So we have the predictions right here. Let's go visualize the model. We love our visuals. Do I still have my plots up? I think I erased my... Oh, there they are. I have them in the viewer also. Let's go visualize our model, though. We don't need these models. Those are our prediction models from 475. Let's go visualize our model. Nice and easy. Visualize model. It's being weird. Oh, did I change the parm flow? Okay, good. Here we are with our model, and this is where it's really clear. Because when you're talking about two mothers who are otherwise identical, what you're looking at here is both have the same length of gestation. But one mother is smoking, which one is that? Smoking now. And one mother is smoking never. And this difference right here, this mathematical difference right here is something like, we saw it a second ago, this mathematical difference between these lines is 241. Like if you take this difference right here, if you take this mathematical difference right here, it is 241. That difference between these lines is 241.322. Mathematically, that distance, because that is the expected difference between two otherwise identical mothers, like they have the same gestation period, mathematically, because the model is all about that mathematics, is going to solve out for the difference right there. That is the mathematical difference between the two mothers who have the same gestation length. We would expect this to be the difference between their pregnancy weights, or weights of the babies. So we've got the summary right here. We've got the overall regression model. Let's do it again. So we're writing out some models again here. And remember, to write the overall regression model, we need to do our formula of this plus this times this plus this. What do I mean? You take your intercept. We'll put it down here on this next line. We'll do some fancy dollar sign stuff. This calls LaTeX code, so you can write equations. This plus, we gotta say birth weight. I think you might, double check if you knit one of these. I think you might want to do this. Sometimes it displays inline text differently, but double dollar signs and single dollar signs might knit differently. Birth weight equals, we're predicting birth weight, the intercept plus this gestation, this plus this times gestation. And now we add in the next variable, but it's a minus. That's why I'm changing it to a minus, because it's a minus. Plus this times this, and there's the indicator. And that's got it right there. There's the equation for predicting overall, just everything in there. But now we're going to go and solve, and we're just going to plug in, because we're going to predict if a mother is smoking never. For the mothers that are smoking never, we plug in a 0 because we would not indicate they're smoking now. And this is the easiest one to solve for because this just goes to 0 right here. So we can just take right here and put that to 0, and there we go. Solved out right there with the values. Let's go and solve for the mothers who are smoking now. And remember, we only put in 1s or 0s here. We'll just be like, oh, they're smoking now, so let's put in a 1 right there. And then we're going to just mathematically solve this, nice and easy. And then we're going to subtract from it. So let's go right here and subtract from it this. We are combining like terms right now by putting this with the intercept. And so now this is the new intercept. And you can actually see behind me that the only difference between these lines are the differences in the intercepts. So once this joins in with the like terms, we see here that it has the same slope, but a different intercept. It actually has a higher intercept for the mothers who are, I reversed these. So these are the mothers who are smoking. Let me make sure I did. Oh, it's a minus. Oh, no, no, no. Error. There we go. Because the mothers who are smoking now should be lower. So double check your work like we just did right there. You'll notice I forgot to do the minus. I was adding it, but the term is negative here. So it's actually subtracting from that. So it's going to be even lower. And it makes sense that it's about, if you look at the mathematics on it, it's going to be about negative 411 because this is minus 241. We plug in the 1 right here because they're smoking now. And then we solve the equation. So double check your work. If they're smoking never, we would not turn on the indicator right there. Find the predictor that is most correlated with birth weight besides gestation using the all correlations. So using all correlations, we can run the baby data set. This will do all correlations, but we want to do sorted equals magnitude. Always double check, make sure it's still sorting down here. This is sorted, and now we see right here the following. We could figure out gestation's most correlated and search through to find certain things. But let's go and do interest equals and put birth weight in here. And this should do it. And now we have gestation is the most correlated, but mother's height is the next most correlated. So kind of, how tall is the mother? That's going to be correlated with how big is the baby. Fit them all predicting birth weight from that predictor and smoking. Oh, let's see. So we're just going to go and take our model to make our lives nice and easy. We're going to grab all the code we have because it's very similar code and drop it in. And then we're going to take mother's height and drop in that instead of gestation. And so let's make a summary. And smoking is even more significant. Still a similar value right there. And the model is going to look very similar again, where we see the two lines with the difference between these lines being 271 right here. The difference between these lines is what we would expect between two mothers who have the same height. They're otherwise identical, but one mother is smoking never and one mother is smoking now. We'd expect the mother who is smoking now to have a baby that is 271.71 grams lighter. Yeah. Predict birth weight from all the variables. So very, very similar code once again with what we're doing right here. If we predict from all the variables, we're just going to drop in here and do a twiddle dot, and this will do every single variable. Now, we can't visualize this one because it just, multivariate visualizations can get pretty complicated and it just doesn't visualize. So unfortunately, we don't get a visualization for it. It's sad times. But we do get the summary. All memes today. Here's our summary right here. Did I do interactions? Oh, no, I didn't do good. We've got a bunch of other indicator variables you'll notice right here, like father race, mother race, or mother education. So you might ask the question, how many levels are there? This is a good test question. How many levels are there to father race? And there's actually 5. Reason being is because one of them, which we don't see, is going to be the reference level. And we could confirm this by going here to levels of baby, father race, and there you go. The first one right there is the reason we don't see it. All of these other ones are being compared to the reference level, and that's pretty interesting. That I don't know. It's the reference level is actually the lowest right there, and then what? It's reverse for. That's so weird. All the coefficients for mother race is negative. All the coefficients for father race is positive. Data is just so interesting. That's so weird that those go in reverse of each other. What does that mean? I don't know. It's just reverse. So we've got all the variables in here, and we got the summary. The coefficient of smoking now tells us the difference between two babies who are otherwise identical. They have the same gestation length, same parents, same parent education, same height of the parents. Everything is identical between these, except one mother was smoking and one mother was not smoking. A little bit crazy to say everything else is identical, but look at this. It is actually one of the few statistically significant coefficients, along with obviously gestation. So this is everything else equal. Like your parents are the same, everything as someone else, education, height, weight, race, everything else equal between two people who are born. we would expect the person who had a smoking mother, that is smoking now, for them to be 232 grams lighter than the mother who's smoking never. And the gestation obviously makes sense too, because we do know how the world works, and longer pregnancies generally result in heavier babies. Statistics doesn't talk about cause and effect. It would rather say two mothers who are otherwise identical. Everything else is the same about them, except one mother's pregnancy was 1 week longer in gestation. The mother who has 1 week longer gestation is expected to have a baby that is 84 grams heavier than the mother who had the 1 week shorter gestation. Lot to interpret right there. What is this? Oh my gosh, no, we don't like prejudice. There's some suspicion that poorly convert to unhealthier and lighter babies. This first line of code shows that the difference in average weights between education levels is statistically significant. However, this is statistically significant association between women's education and smoking, so we shouldn't simply compare birth weights of babies for each level of education without also accounting for mothers' smoking habits. So this is about the drop one right here, which is going to do a partial F for test for us. Determine if the variable mother education is statistically significant in your model from Q5. Is there any differences in average birth weights between the levels of education after accounting for other information in the data set? So what is a partial F test? Partial F test is when we remove out a certain number of variables in the model and we compare it to the full model. So a full F test goes from the naive to the full model, but now we're going to start with variables in the model. You might say, well, why do we need to remove out variables? Mother education right here has multiple levels. Mother education brings with it 2 indicators. That means mother education has 3 levels, and we can confirm this by going down here and looking at it and going to mother education. It has 3 levels because 3 levels creates one reference level, and 2 indicators. So just there we go, 1 reference level, 2 indicators would be created when we have right here 3 levels to a variable. 3 levels to a variable, 1 reference level, 2 indicators. That's the way it works right there. And below high school was the reference level. So if we're asking, does this bring with it new information? Well, the original model right here, and this is the model with just mother education. There we go. It looks like they are statistically significant. But looking at the drop one test right here, it is still statistically significant. And I'm pretty sure it wants us to compare it to the previous model we have up here with everything in it. So after we control for all the variation of every other variable, which we have our full model right here, we can run the drop one here, and you're going to get a lot of results with this. Oops. We can run the drop one right here. And with the drop one, you'll see mother education. We need to do test equals F. Forgot that. And mother education is not statistically significant. So after controlling for all other variables in the model, and this removes out both levels of indicators, mother's education does not bring with it new information not accounted for by the other variables in the model. So it's redundant in the information. So maybe there's some overlap in whether people choose to smoke or height, weight, some sort of overlap, which could be measured. We should mention this by the variance inflation. Ooh. And there's very high variance inflation between, race right there, and mother age has some father age. Probably seeing, people of similar age marrying and stuff like that. But this is once again real data, and so there's high variance inflation between overlap. And this is a multivariate overlap, so it's not just 2 variables overlapping, but sometimes 2 variables contain a lot of the overlap. So looks like we have a lot of overlap there. Smoking is very unique in the information it brings. The lowest the variance inflation can be is 1, which means it's not inflated at all, and you'd have to have no overlap. Gestation is actually super unique also. Gestation brings, and it does very unique stuff, like how long are you pregnant for is not really associated with your age, race, education, height, weight of any sort of thing connected to the mother or the father of a child. Pretty interesting right there. No overlap. Let's look at our check regression right here to see if our model is actually doing what it should do. When it comes time for check regression, and to see if your model from Q5 looks valid, is that the full model? It is the full model. So when we do this from all the variables, cool. We have our full, gonna be crazy right here. With the extra equals true, we're gonna get a lot of output. And if you ever knit and you want to remove stuff, let me know. Now this is where sometimes people get stuck right here. is when you run this, you have to hit enter. Hitting enter will show the additional plots, because if you try to type code in right now, the code's not going to run. So don't type in code, just hit enter, and we can see what's going on. We'll take a look at these plots here in a second. Lots of plots, and we should be done. There we go. The big thing to look at first is the p-values. Now, we get a lot of NAs right here because we can't do it for categorical variables because we don't really have linearity for those. We have a problem with the linearity of gestation, and remember, any p-value below 0.05 is a problem. We can't check these. We don't have problems here. Actually, so wow. We only have problems with the normality of the residuals for the overall plot and for gestation. So here's the overall normality, and that's not that bad. Like, that's actually pretty good. It's probably due to a large sample size. So overall, this is pretty good right here. I'm not worried about this. Let's go look at the linearity of gestation. There's maybe some non-linearity towards the end. We'll expand this. It might be picking up on this, but it's saying gestation does not have a linear pattern. I don't really see it much. That line goes pretty through it. And once again, the reason we can check this is because our sample size is 553. So overall, I'd say the model's pretty all right. Once again, the steps are check your p-values. We had a problem here. We can't check these categorical ones via this methodology. We had a problem here because it's below 0.05. Sample size was above 25. Looking at the normal probability plot right here, we see it follows the red line pretty closely. So I'm not really worried about the normality condition right here. Like I'm almost shocked it failed. That's pretty darn good. A little bit of an issue there. Tiny bit of an issue down here. Like very small issue because it's outside the kind of meh lines. But tiny more of an issue here, but not big. Not really worried about that. And then last but not least, the gestation. Does the overall... the overall, the linearity was fine for the overall model, I think. Oh, overall model cannot be checked. To check the overall model's linearity, which is right here, you have to have duplicates. So you have to have repeat observations. So we might, if you look at the pattern of the residuals in the gestation, it actually looks similar to the overall model. There might be a little bit of an issue with the overall model's linearity because gestation is where a lot of the information is coming from. So this model's got small problems. Well, all models are wrong. Some are useful. This model looks pretty good. We should have really looked at that R squared right here because how's our R squared and our R squared adjusted? Only 30%. Model has some application, 30%, and we typically miss the birth weight of a baby by about 441 grams, which is close to 1 pound. So if I say you're going to have a 7-pound baby, probably about 6 to 8 pounds. Not that bad, right? 7-pound baby, 6 to 8 pounds. Pretty decent typical miss. Probably better than just the naive model, which would just say, all babies are 7.5 pounds, the average weight. And the R squared adjusted because of how many variables we have in the model, not too bad. It is a bit of a difference. I'm a little bit concerned. That's about a 3%, but 10% of the original R squared is lost or so, about 8% maybe. One thing you can do with your R squared adjusted is compare it and see how much of your original R squared is retained, and we're down to about 91% of our original R squared. You want these numbers to be as close to each other as they can because this is the penalized R squared. It doesn't have an interpretation. It's your R squared after you penalize yourself for adding in all these variables right here. It's probably not the best model we could make, but it's not a horrible one. It's not horrible. So with the influence plot right here, we're going to see if anything has undue influence on this model. Are any of these points in this model kind of really controlling what the model is doing? And we're going to use the Q5 right here. And we have baby 553, which might be that baby right there. Print out the row 553 to find out what's going on. It's one of those. It's either this one, this one, this one, or this one. These are the 4 influential babies. Now, the size of the circle right here is the size of the influence. You'll see right here that these babies are very unusual in their characteristics. The more leverage you have, the more extreme you are in your values of X's. And the more deleted studentized residual you have, the further you are away from the model. And definitely review what a deleted, meaning you are removed to make your residual. Studentized, meaning we standardize the values. Hence, -2 and 2 are 95% of where we would expect the deleted studentized residuals to be. And residual means how much the model misses by. So that one is the most influential by size of circle. You'll notice there are a lot of points that are not popping up here with X's that are kind of influential. This model has a lot of kind of influential points, so maybe they're kind of balancing each other out. But baby 553 was super influential. Let's go here to the data set and go to row 553 and maybe take a look. We probably want to look at the summary. Let's see right here. This baby, which is very influential, had a birth weight of the following. Is that very big? That seems very big. Oh, wow. That's not very big. What am I saying? Are you serious? Is that the lightest baby in the data set? Wow. Let's go to a summary. I don't think many babies are lighter than that of the baby and go to birth weight. That is the lightest baby in the data set. That's the lightest baby in the data set. Now, that would probably go more towards them being far away from the model's prediction, which might explain that. They're going to be kind of unusual in their X characteristics. The gestation was 30, which is going to be an unusual X. That's probably a very low gestation. So they're far away from the mean. They might be the lightest gestation. Yeah, they have the smallest gestation. Mother was 35. Mother's height is 5'5". Mother's weight is 140. Probably a lot of their unusualness. Father might be a little bit heavier, which would make an unusual X for the father. Father is towards the maximum weights in the data set. So this child right here is a little bit, they're the lightest baby in the data set, 3.6 pounds, or 3.46 pounds. That gives them a very probably far away from the model because it's going to be harder to predict someone that's an unusual occurrence like that. And then also they're unusual in what their parents have as their X values. That's giving them the leverage on this right here. This is the X's right here because on the X-axis. And then the distance right here is the distance from the model, basically. So that baby right there is kind of a decent mix of unusual combination of X's. Mother having a very short pregnancy, father being quite a bit heavier. Interesting that the average weight is 171 right here. Maybe that's how much people weigh on average. I don't know. I don't know data. So that's pretty unusual right there. Let's load in the tips data set right here and do a little more data. Load in the tips data set, investigate whether there's a difference in the average tip between smokers and non-smokers. So we're going to look at some smokers, non-smokers again. And let's make a model right here where we see we're doing tip. Let's look at the tips. And, might be. Can I go to glance? You might not have glance. I can't do glance. Augment. Let's do augment. No, it doesn't like it. Extra codes from extra packages. Are we doing tip or tip percentage? We're just doing tip, right? There's an average tip. So it's tip between smokers and non-smokers. So we want to go here to tip from smoker from data equals tips data set. There we go. Fit a regression. All B. There's the answer. And there we go. And let's take a look at the summary. And let's see who tips more. The answer for who tips more is smokers. Smokers are tipping more, but this difference that we're seeing could be due to p-value right there. So there is a difference in the tip percentage of about 0.4%. One thing you might say, that's small. I don't care about it. Well, more so than us just not caring about it because it's small. It's probably just due to random chance. It's super likely that these differences, because you have some people come in, tip a little bit more, some people come in, tip a little bit less, and these differences right here are probably just due to random chance. Why am I saying probably, like very likely? High p-value. And it's not always just because differences are small. Like if I told you, once again, we're talking about birth weights of babies and talking about differences of just a few grams. If I tell you I'll give you like 2 grams more of steak, you'd say, 2 grams more of steak, I can't even tell the difference. But when we talk about tip percentages, maybe over the long run, it matters. Like you'd wait on 1,000 tables a year. Well, then 0.4% more tip at a fine dining restaurant would be a great way to increase your tip. But these differences are probably just random chance differences. The difference could easily be 0, as in there's no difference between it. Line could be flat. So it might be the case that is only apparent after accounting for the variability in tip percentage attributed to bill amount. Find a model predicting, and are we doing their interaction? I think we're going to do their interaction down here in a moment. Who leaves what is the difference between, go. So many more. Let's do it. We got time. Here we go. So let's see. Right here, we need to make another model. And let's make our next model right here. And we need to do bill now. So we're just going to add in bill right here. And running the summary right here on it. We see smoker is still not statistically significant. So comparing two bills tables at a restaurant that are otherwise identical, we do see a difference. That difference we see between them is negative 0.23. That's the bill difference. The slope is very significant with these models. But the differences between smoker and non-smoker, where smoker, yes, is expected to tip more, could once again be due to random chance. So this right here is not a statistically significant difference. We are not seeing it. But now let's use all the variables in the data set. So this is very, very similar. It's the twiddle dot. And after accounting for all other information, who leaves the highest on value tip? Smokers or non-smokers? And right here we see, whoa, wow. Didn't see that one coming. Now it brings with it new information. And smokers, after accounting for otherwise identical tables, two tables that are otherwise identical, but one is smoking, the other's not smoking, the smoking tables are leaving higher tips. So if it's like the same day of the week, the same time of the day, same size of party, same bill amount, same tip amount. It's interesting that that's being included because tip amount would definitely be correlated with tip percentage. Like how much did you tip? That's going to be correlated with tip percentage. And same gender of the individual, which gender right here doesn't matter. It's not statistically significant in this model. Yeah. One question I want to ask, though, is how would we find out if weekday is significant? This is a review question now. To find out if weekday is significant, we would need to go in here and do a drop one to remove just one of those from the model. And weekday as a whole is almost, but not quite statistically significant. Notice how smoker, because it brings with it one indicator variable, has the same p-value up here, because you can take one thing in and out of the model, but you cannot take multiple things because weekday has with it 4 levels. It's only Thursday, Friday, Saturday, Sunday for this model, Friday being the reference level. Review question right there. Fit a model predicting bill, not tip percentage, from party size and weekday. So let's go right here. Predicting bill from party size and weekday. There we go right there. And write out the implicit equations. So when we write the implicit equations, remember once again how we do it. We always write out by starting out writing the full equation. We are predicting bill, which is the y variable, y equals this, and then we just go plus, we do the next coefficient, 5.5593 times whatever the x variable is, party size, plus, and then we do the next coefficient, 0.995 times weekday Saturday, just abbreviating right there, plus 0.1621 times weekday Sunday, and then we'll do Sunday right there, plus or minus, because it's a minus down here. We're just going down this plus this plus this times this plus this times this. And then we go right here and do 1.3943 times weekday Thursday. And if it is Thursday, we put in a 1 right here, and we change all these to zeros. And we do that for every day, whether it is that day or is not that day. If it was equal to Friday, we'd plug in zeros for all these, and we would just reduce the equation. Good stuff right there. Among equally sized party, what is the difference in average bill among Sunday and Friday? So that is just going to be the coefficient right here. Remember, once again, the reference level is what we're comparing everything to. So this is the difference between 2 days that are otherwise identical that have the same party size. We expect the difference in bills between a day on Sunday and a day on Friday to be 0.16. 2 days that are otherwise identical, but one day is a Sunday and the other day is a Friday. The difference between the bills is expected to be 0.1621. And after accounting for the size of the party, on which day is the average bill largest or smallest? So if you look right here, Friday has a coefficient of 0. Remember back to our beginning examples. With Friday having a coefficient of 0, you can see right here that Thursday is the lowest day. And one really good thing to do is to visualize your model. If you visualize the model, it might be a lot to see. But remember, Thursday is the lowest, and that's the blue line. Friday's right here with a coefficient of 0 because there's no change to Friday. but Saturday is the highest. So visualizing the model, hints for the take home for the final. Visualizing your model can definitely get you the answers, because we can see right here that Saturday, I think, is the highest, right? And there's Saturday with the red line up there. Sunday is very close to the black line, which is the reference. Black line's always the reference, first alphabetical. And then the lowest right here is Thursday, because it's that much lower than Friday, and visualizing can help. Among equally sized parties, the difference in average bill amounts among days statistically significant. Hint, use the drop 1. So once again, we have 3 values here we need to drop out of our model. So all we're going to do is the drop 1. Now, for a quantitative model, quantitative Y, we need to use test equals F. For later on, when we do logistic, we'll do test equals chi-squared for this. So the second argument is not always going to be test equals F. And you don't want to look at the significance of these. If you notice, the variable itself is actually more significant than the indicators. The indicators are how statistically significantly different they are from the reference level. And the one that is closest to the reference level is Sunday. And look, Sunday has the least significance. But that's only because we're comparing it to the reference level. I'll do one last thing here, which is not required. But if I went to my tips data frame and got the variable weekday, and went to it and re-level tips weekday, and we want to put here, let's go to, what's the highest day? Saturday. I think this should do it. This is not something we generally do. That re-levels it. Let's store this. What I'm going to point out here is that now I am re-leveling the reference level, and you will see that we get different significance among the indicators. So we're going to re-level this. We're going to go to tips weekday. This is not something we generally do, but we can reassign the reference level. And now Thursday is statistically significant because it's the most different from Saturday. But the thing is, when we rerun the partial F down here, the p-value on the partial F for this model is still the same. So the p-values for the indicators are how different are they from the reference level. And if I visualize this, you will see we have a new reference level for this model. The reference level now being the black line, which is not first alphabetical because I re-leveled it, not something we generally do. But with this right here, we notice that these p-values, Rock knows the answer. It doesn't matter. These don't matter. They are the difference from the reference level. They are the difference from the reference level. How do we find the significance of a overall categorical variable that has 2 or more indicators? We look at the p-value for the partial F. And that's got it, everybody. Great work. A lot of good activity right here. Wanted to end right at noon. Hopefully this helps everybody out. Ask questions if you got them. Keep up the great work. I'll see everybody later. Bye for now.